His bachelor's, master's, and PhD from MIT. Great choices. He was a professor at University of Illinois at Urbana, and he's now for many years been a professor at Northwestern University in computer science department. He's one of the fathers of qualitative physics, and I've collaborated with Ken on books and everything else. So welcome, Ken.
Thank you.
Now, is Barney Pell here? Oh.
Hi. Yeah, in fact, what Johan didn't mention is one of the first ways I got to know him was he was a graduate advisor in my dorm as an undergraduate. But actually, even before that, I got inspired to be in AI and actually winded up at MIT because, and I'm going to try to do two things. I'm going to first do a little bit of archaeology, okay, because people who work with Danny a lot, I've only worked with him on one project. DARPA's one attempt at doing middle school and high school education. Didn't last very long, as you might expect. So I'm going to go back to the very beginning of his PhD thesis, student, okay? And I'm also going to sort of show you where things are right now and try to hopefully help you get some of that sense of wonder and just realizing just how far we've come and how interesting things are going to get. So, let's see, this has a laser, I think. No, it doesn't. Oh, well. We'll live without that. Well, there's a button that's got a little red thing. Yeah, that part's dead. That's all right. Oh, my God. Oh, right. Is this green? Can I burn holes? Far out. Look out, I'm armed. All right. So I first got interested in AI in part because of Danny. When I was in high school, that really is dead. Okay. When I was in high school, I scammed my way into classes at the University of Arizona, okay, because they had computers there. And they had something else, too. They were a federal repository library, right? Because in case of nuclear war, you'd want to rebuild civilization, and so they put copies of all sorts of books all over the country, at least one federal repository library per state.
You wouldn't want to rebuild it in Arizona.
If that's all you got, that's all you got. So what the hell, you know? And so there were all these books on AI, right? Way more books, right? And so I started reading, and I read about student. And I was taking a programming class. We were programming an IBM 1130 with punch cards. And I really wanted to do for my term project an implementation of student in Fortran, okay? And that didn't look feasible. I ended up doing a checkers program instead. But boy, this really got me thinking. And I kept thinking. And if you think back on other people you've heard talking today, they've said the same thing, that the student was this really interesting program. And it really was one of the inspirations for them getting interested in the field and how intriguing it is. So let's take a closer look at that. You can find the whole thesis online at MIT. It's been scanned. So there's the title. You see it's 44 years ago, 1964. And take a look at who was involved. Marvin Minsky, Herb Simon, Noam Chomsky, and Seymour Papert, three names you don't see in the same sentence very often, in terms of a positive contributing way. Okay. All I can say is there must have been many fewer grad students then, okay? Because to get time on these people now, next to impossible, especially Herb. And you had to justify, of course, why in heaven's name you'd want this computer to do English. So there are many tongues the computer already understands. Remember when you know, we had this metaphor of a computer language, and it was like a language that we speak. It's like a natural language. And the same thing with metaphors. When you first get a metaphor, you start taking them very seriously. When Rutherford had the whole atom and solar system model, first thing people did was they started looking around at electrons to see where the little moons orbiting them, just like there's moons orbiting planets, right? And so you had graduate schools in the United States saying, well, we're going to get rid of the foreign language requirement. You can learn a computer language instead. Great thing for techies, not so good maybe in terms of the analogy. But there's this very key point here. If you actually can learn how to make a computer understand the natural language, we'll have taken a big step towards creating an artificially intelligent computer, and that's right. as far as anyone can tell, if you look at things that, why we're smart, why we're different than gerbils, okay? Gerbils can navigate in the world. Gerbils can do all sorts of clever things. But in fact, they live in our cages, not the other way around, okay? And so language is really important. And so understanding that really is telling us something deep about ourselves. So here's an example of student in operation. So here's the problem, and it's of course written in Lisp, as you can see, the language God meant AI to be done in. The distance from New York to Los Angeles is 3,000 miles. If the average speed of a jet plane is 600 miles per hour, find the time it takes to travel from New York to Los Angeles by jet. Okay, natural language input, and look, natural language output. The time it takes to travel from New York to Los Angeles by jet is 5 hours. Whoa, okay. Most people don't use natural language input on their systems today, okay? That's depressing but true. And we're going to come back to that in just a few minutes, okay? And now, in addition to this, it said, okay, it got these equations directly from it, but you have to have some world knowledge. Global knowledge was used to fill in the gaps, okay? A little bit of world knowledge, a little bit of common sense, okay? And again, we'll come back to that. Now, of course, today we know computers can do algebra, right? We buy programs to make them do algebra. You can pay tons of money and get Mathematica, you can buy Maple, you can buy whatever. There's freeware versions of these things. They do algebra way better than humans do, okay? Not a big surprise, okay? Now, if you look at the evaluation of this program, one of the things Danny suggested was, well, since people are doing this and you're doing the same kind of input as people, using the same kind of input for the simulation as you're doing for the original people, and since the entire process was programmed, we can use a measure of comparison between the performance of student and humans on the same problem. In fact, an IBM 7090, which of course is slower than your digital watch, answers most questions that it can handle is faster than humans trying the same problem. But of course, the 7090 can perform over 100,000 additions per second. Whoa, feel the surge, okay? So whole labs were operating and trying to do AI research on machines that today you would think, what an underpowered cell phone, okay? Now, if you look at what's happening today, of course, there's a whole boom business, cognitive science research. You take that human software comparison very seriously in terms of cognitive simulation. You build a simulation of something, and you compare in detail, sometimes, in fact, times and reaction times, and you have some mapping from computer speeds or computer operations to human operations, sometimes more at the level of content models. And so again, this has turned out to be a big boom business. In fact, computers can teach algebra in part because of that kind of boom business. So if you look at Carnegie Learning, and their advertisements say helping more than 500,000 students in over 2,600 schools succeed in math, that's per year, okay? So they sell the cognitive tutors to whole school systems, and boy, do they sell. Are your students ready? Algebra ready? Okay, I am impressed by the business world. I have no desire to be in it, but I'm very impressed by it. Now, the cool thing is, if you look at what's under the hood, it's a cognitive model of people doing algebra. It's ways to do algebra correctly, and there's multiple ways to do it. So they model them all, and they model misconceptions and ways things can go wrong. So at any point in time, when a student is doing something, they can track what the student is doing and estimate what their knowledge is and give feedback that's targeted to the student, which is why these things work so well. So if you take a look at the input here, well, you've got the problem stated in English, and you've got a worksheet and graphs, and the student is actually typing in things here. And over here is a little skillometer, which Danny might remember from Katie days, because our system had a skillometer too, from Ken Kadinger, the same guy who did the Carnegie tutors. And so you could actually look at how you're doing on each of the skills involved in doing this kind of operation. So it really is using a cognitive model there to help teach in the way that an ideal tutor might help someone learn. Now, let's calibrate you, okay? Because AI people don't always take the need to do these sort of experiments terribly seriously. So, there's, of course, a lot of lore about story problems, and here's Hell's Library, right? The big book of story problems galore, etc. So here's the same problem expressed in 3 different ways. Here's a story problem version. As a waiter, Ted gets $6 an hour. One night he made $66 in tips, and there are a total of $81.90. How many hours did Ted work? Okay, so that's a story problem. You're telling a real-world story. Word problem, starting with some number. If I multiply it by 6 and then add 66, I get the number of the beast. I get 8190. What number did I start with? Equation. 6 times 6 plus 6 equals 8190. Okay, how many think the story problem is easiest for students? How many think the word problem is easiest for students? How many think the equation problem is easiest for students? Okay, now it turns out we know the answer. Surprise, the story problems are the easiest. Okay, and the word problem is next easiest, and by far the hardest is the equation problem. That's Matt Nathan and that's Ken Kavinger, the guys who actually did this research. Now, interestingly, you can console yourself, those of you who got it wrong, because the more experts you are, the more likely you are to make that mistake. Okay? So if you look at the number of teachers who get it right, well, about 40% actually get the correct ordering, right? Because the mythology about story problems is pretty prevalent. But about 40% of elementary school teachers actually understand that equations are going to be the hardest. Middle school teachers, they tend to be a little bit more expert in math. It goes down. High school teachers, well, okay, they're sort of like us, right? They just get it completely wrong because it's hard to model yourself. And that's why people do all these very careful experiments, because it's very, very hard to really understand what's going on inside your head. And again, if you look at some of Danny's work on social sciences, you see echoes of this. Knowledge bases. Student needs access to a store of global knowledge, not specific to any particular problem, and can retrieve relevant facts and equations from the store of knowledge. So I went through, I mean, the whole thing is there in the appendix. So students' knowledge base had 52 facts. Okay? 52 facts, it does a pretty good job. Those include the lexicon, like plurals of words, okay, as well as equations. Okay? 52 facts. By the 80s or 90s, people were up to 100, a couple of hundred, maybe 1,000 or so facts. Okay, but small numbers of thousands. Today, you can go to SourceForge and download the OpenPsych knowledge base. It's about 2 million facts. Okay? When we suck it out, the flat files we put up on the web, sucked out of it, it's 1.8 million facts, but we leave out a lot of stuff that they have in there because we don't think it's very useful. But if you download it from there, bingo, you got 1 million facts. And if you look at what's probably going to happen if we all succeed in doing what we're doing, systems are going to get even bigger. They're going to get more like 10 to the 7th or more like 1 billion facts, and those aren't going to be hand-entered. Because we're hitting a point now where we can start bootstrapping by a combination of things, learning by reading, using natural language, sketches, vision, robotics. You're going to build systems that have experience. Now Did we get there? And I think the robustness of human beings comes about from experience. And that's a lot of concrete, specific stuff that then you generalize partially and slowly via an analogical processing. That's our bet anyway. And if you look at how come we're so robust, we've dealt with the world a lot. And language is going to be, I think, one of the ways that you actually get the moral equivalence of experience into systems. It's not the only way, but it's one important way. That's caused us and other people to really start doubling down on natural language understanding as a bet. Disclaimer, my group are not hardcore natural language researchers. We are not linguists. We do not play them on TV even, okay? We are trying to be users of natural language as a technology. Now, if you look at Danny's thesis, the student comments on its progress in solving a problem and can request the help of the questioner if it gets stuck, okay? A little tiny touch of what became eventually interactive dialogue. So if you look at James Allen's beautiful work on the plow system, for instance, as part of the CALO program, the evaluation paper they had at last year's AAAI was amazing. They had tasks where you're teaching the system by a combination of showing it and natural language instructions. Natural language, spoken language, was giving you rationale for what's going on. They had people choosing multiple systems to do tasks with, and they were training the systems on how to do the task. They had different people using different systems, and they pick which system they prefer. In other words, it's just really amazing how far this has come. I keep waiting for those to be bundled into somebody's operating system, okay? It'd be a lot of fun. But then again, I love torturing machines, as you'll see. we've been doing our own work in the area, learning by reading. So we've been using Chris Riesbeck's direct memory access parser using simplified English and trying to build up knowledge about world history and politics. Actually, given the sponsors, it's sort of things happening in the Middle East, as you might expect. We're starting with the research psych knowledge base, and this is off the shelf. Okay? If you had to start from scratch and build a knowledge base, then you're going to get 52 or a couple hundred facts. But you don't have to today. That's a big change. So if I can just go to the web and download a 1,000,000 fact knowledge base as my starting point, life is different. Okay, a small group of people can build a system that can, for instance, read a bunch of stuff, ruminate over it. The system actually sits there and thinks about what it read offline, asking itself questions. Okay, and we've shown the thing actually can learn by reading. We gave it a quiz, and it was 10% right before it did any reading. After reading, it went up to 37%. And after reading with rumination, it went up to 50%. So you actually can build things that can learn from simplified texts.
Were the questions in the quiz written by people who didn't know anything about psych?
No, they were automatically generated based on the parameterized templates. So we went through and said, okay, so this question has an agent in it. So we take all the agents that were mentioned in the texts, and we said, let's make all these questions about those agents. And so automatically generated. Our goal in this sort of project is to never know the underlying representations. So for instance, in doing the reasoning, the axioms used were automatically extracted from psych, knowing the kinds of questions we're trying to answer, the current distribution of facts in the knowledge base, and the kinds of facts you could get directly from reading by analyzing the patterns that DMAP used, which again were sucked out of the psych knowledge base. Okay, so again, it's got to be all automatic. Now, you can also start using this in a very practical way. So I do a lot of cognitive science work, and one of the things we've been doing is trying to avoid what's called tailorability. What usually happens is you have some stimuli you give people, you run experiments, and you get some human results. Then you hand translate that into predicate calculus, and then you run your cognitive simulation, and you compare the two, right? Now, the problem is if you're doing this and this, there's a chance that the choices you make here are based on knowing what's going on in here, and that's called tailorability. You might get reasonable results, but because you use very ad hoc, cranky representations. The more you can make this process automatic, the more you reduce tailorability. So what we did was we actually took a bunch of off-the-shelf parts. James Allen's parser, right out of his textbook, Comlex lexicon, research psych knowledge-based contents. The psych engine is fine for some things. We suck the knowledge out, put it in our own engine because ours are better for things. Discourse representation theory to actually handle a lot of contexts and modals. And now we can do things like this. We have for instance, one of our projects, we're modeling moral decision making. I don't want to go into that because it's a big, complicated issue. But things like sacred values and how people aren't always utilitarian in their reasoning. And we can actually model the results of several psychological experiments from the literature in moral decision making. And the stimuli are put in by simplified English. So here's an example of something that was rewritten from an experiment. A convoy of trucks is transporting food to a refugee camp during a famine in Africa. 1,000 people will die in a second refugee camp. You can save them by ordering the convoy to go to that refugee camp. The order will cause 100 people to die in the first camp. Turns out most people will not give the order, because you then directly will be causing the death of those 100 people. Okay? And you can play around with this, and some of the answers that you get in these experiments are determined by people's culture. So you have to be able to model things differently based on the cultural rules and values. And one way of getting at those indirectly is by looking at their fables and life stories. And in fact, we're collaborating with psychologists and anthropologists who are working with a bunch of groups, often different tribal groups in the same area, like Northwestern Americans, you know, and people like that. And so we can actually do that kind of modeling. Now, again, off-the-shelf performance these days can be pretty interesting. If you know about Mobius, you'll laugh. Because of a dam on the rivers from another moral decision problem, 20 species of fish will be extinct. And so here's a description, and you notice that we didn't have to instantiate 20 extinction events, or 20 species, right? It just sort of gets it all right. And this is just one grad student hacking around. Now, the one grad student that come up with all the ideas, no way. But progress in the field is such that if you go off and read a bunch of these papers, you can make stuff that does cool things. At least some of the times, okay? When it's good, it's really good. And in fairness, it has plenty of blunders. So for instance, I tried a bunch of sentences from student, and not one of them would work in our system. Okay, I sent an email to Emmett. He thinks he understands what it is, and they're all going into the regression test. So a few months from now, it will work. Okay, but right now, you get some hilarious things. So the gas consumption in my car is 15 miles per gallon. Gets the gasoline and miles per gallon, but it thinks the car has tuberculosis. Okay, because consumption is one of the readings for tuberculosis. Okay. So there are glitches. And by the way, we have plenty of them in the learning reader too. One of the things we have a lot of fun with is figuring out when the system's made mistakes. So here, the Jordan River flows in the Dead Sea. The result it gets is this is entering a container, and the container is Grateful Dead, the musical group. Okay. Now, by the way, these are very funny, and you get lots more funny errors, believe me. But these are mistakes that you couldn't even make before. Because who the hell would type in Grateful Dead? And who would lexicalize them? But if it's there already, that's useful. Okay? So it's a sort of mistake a human would make if they didn't know very much, right? So if you think about yourself as building a six-way idiot savant from Mars, okay? That's sort of what's happening here. Okay. Now even though language technology is nowhere near finished, and Barney will tell us all about the latest in that, you find people incorporating bits and pieces of it into everyday applications anyway. So when I was cutting and pasting from the thesis, that OCR's thesis, I basically was using OneNote, and OneNote at one point says, instead of just copy text from picture. Ooh, that's cool, okay, because I could barely read the darn thing. So what the heck, okay. Gave it a try. Now, it's far from perfect, okay. Understanding is particularly poignant, okay? But if you think of this not as, oh gee, it's another buggy Microsoft product, but if you think of it as, okay, it's kind of like a puppy trying to get you the paper, okay? It's gone off into this image, it's trying to bring back what it can, and it's imperfect. It's by no means perfect, but it's still more useful than doing it all yourself. And that's the way it's going to go. We're going to climb these curves slowly, and we have been climbing them, and things are getting more interesting because of the machines getting faster, and there's lots more ideas, and there's lots more stuff off the shelf. And the more we can make those off-the-shelf parts extendable by everybody, the faster the progress will go. So to me, I'm very excited. I think 50 to 100 years from now, people are going to look back on this as a kind of golden age for AI and cognitive science, and the best is yet to come. Because this is a time when we're just able to do things now that we never could do before, that nobody could do, and now even small groups can do them without monstrous resources. And if you think back and you look at it, some of the important seeds were planted 44 years ago in Student. Thank you, Danny. Any questions?